Hi, everyone. So today I'll be talking about security aspects of machine learning, in particular adversarial examples that some of you might have already heard about, but I'll give a brief intro to this problem, and then some recent work on the defensive side and the attack side that we did over the past few months with a number of collaborators. Nicholas Papernot and Patrick McDaniel from Penn State that actually gave talks at this very same event yesterday, I think. So you might have heard them talk about other very interesting projects. Then also with Alexei Kurkin, who's a researcher at Google Brain, and Dan Boneh, my advisor at Stanford University. Okay, so let's begin. So this is the setting we consider here, and you might have actually seen this image before. It's become sort of the reference image to talk about this problem of adversarial examples in machine learning. And so what we see here is on the left, it's an image of a panda. I hope you agree with me on that. And if you feed this to sort of a state-of-the-art machine learning model that was trained to recognize a variety of classes of images, it should be able to recognize that this is actually a panda. And what some really nice work by, first by Christian Szegedy and his co-authors, and then Ian Goodfellow and his co-authors about 2-3 years ago, what they showed is that although these models actually have learned something useful in the sense that they can actually classify a bunch of images correctly if you feed them to the model, you can also very, very easily find these sort of imperceptible perturbations that you see here in the middle that give you an image on the right that to the human eye looks exactly the same. And yet the same model would actually tell you that with sort of 100% confidence, it believes that this image now represents a gibbon, which is a sort of small monkey. And this sort of problem, this lack of robustness from machine learning models seems to be somewhat ubiquitous nowadays. So in particular, there's been a whole lot of work in the research community about showcasing these problems with image classifiers. Work is mostly focused on images because it's so easy to show this problem. You can just show like 2 images that look exactly the same to us, and where the model makes misclassifications. A very recent line of work that was particularly interesting was in showing that you can actually make these perturbations sort of translate to the physical world. So you can perturb the pixels of an image so that the model misclassifies, and then you can actually print out these images. This is what you see in the top right. This is from a nice work by Alexei, one of my co-authors, where they actually printed out these images, then scanned them again with a digital camera, fed them into a model, and got them to be misclassified. Other work in this space sort of has looked at other types of sort of physical artifacts. So either here on the top, you can see a really nice work by Lucho Bauer's group at CMU, where they printed out these sort of weird-looking glasses that fool facial recognition systems. So here, with these glasses on, Lucho is actually recognized as a famous actress instead. And there's actually some debate right now going on about whether these attacks could actually be problematic for self-driving cars. So there's some ongoing work about trying to figure out whether the type of models that would be embedded in cars could actually be fooled by something like these stickers you see here at the bottom on stop signs. So far, it's not clear yet, in the sense that these models actually do a lot more than just classifying a single image. They sort of will look at things from different angles, different distances, and sort of aggregate all this information together. But there's some preliminary work that's kind of promising in showing that you can actually make very robust perturbations that fool machine learning models while not being particularly harmful to humans. This has also gone beyond the realm of just images. So there's been a bunch of work showing how you can do this for malware classifier. So here it gets much closer to sort of tangible security problems, where essentially, as an example, I take this work from Gross and her co-authors from last year, where they took a malware classifier for Android applications, and they found that just by modifying a few entries in the manifest file of the application, so really changing a few things, some metadata that really doesn't affect the application's behavior, they could get a state-of-the-art malware detector to just completely misclassify things as being either malware or not. And then more recently, there's also been some very nice work showing that you can fool text understanding systems. You can fool speech recognizers such as Google Voice using these similar techniques of just producing examples that a machine learning model will classify completely differently than a human would. And this sort of seems to be a problem for secure deployment of these machine learning models in practice. So how do you go about creating an adversarial example? So here I'll just give a very brief overview so that we know what we're talking about. So you start with an image, and here you know what classifier you're dealing with. So you feed this image through a classifier, you get some distribution over output classes. And given that you know the true label, in this case a bird, you can compute some kind of loss. And the way you would train this model is just to try and minimize the loss that the model incurs over a bunch of training data. And what we can now think about how we would create an adversarial example is we can sort of take every single input that makes up this image, so every individual pixel, and sort of ask what happens if I just nudge this pixel a little bit. And maybe if you nudge this particular pixel in one direction, you'll actually have the loss go up. And that's sort of good for us if we want to make an adversarial example. Then you can sort of ask this about every single pixel, and for some of them, the loss might go up, for others, it might go down. And if you just aggregate all this information for all the pixels that make up your image, this is actually equivalent to just taking the gradient of the model's loss and just moving into that direction. So sort of doing the analog of what you would do when training a model with gradient descent. Here we're actually doing gradient ascent in the sense that we're trying to maximize the loss by just moving every pixel by a small amount into a given direction. And there you'd end up with a perturbation that might suddenly make your loss shoot up into very high values, which is sort of equivalent to saying that your model misclassifies the input image. And so this previous slide at a sort of white box threat model, where you know the machine learning model you're attacking, which could be a very relevant threat model if you might have, say, your own self-driving car that you might try to reverse engineer and figure out what kind of models being run in it. But more often than not nowadays, machine learning models are run on the cloud or even in maybe other people's self-driving cars to which you do not have access to. And so in that case, the prediction model is kind of a black box. You can't just go and figure out the gradient of the model analytically. It turns out, and that's kind of what makes this problem really interesting and really hard from a security perspective, is that you can actually very easily attack these models without even interacting with them. And the way you would do this is you basically just train your own model for a similar task, or say the same task that the target model you want to attack. Then you create an adversarial example for your own model, completely disregarding the models you actually plan on attacking. And then you're going to send this adversarial example to these other models and sort of hope that they will also misclassify. And it turns out that this actually happens with very reasonable probability. And the way we say this is that adversarial examples tend to transfer or generalize across models. And this is somewhat surprising. It's basically telling us that not only do the machine learning models we train today have these kind of blind spots that we don't really understand that well yet how they actually occur and why these models are so fragile to very well targeted perturbations. What's even worse is that different models that might have different architectures that were trained independently with different random seeds on sort of similar training sets, so to solve a similar task, they seem to have blind spots that kind of intersect, and so you can target models you've never seen before just by targeting one or more models that you have seen. And so this is sort of a much worse threat model in that sense. So how about defenses? Well, here's where things get a bit murky in that there's actually a very large number of things that when you first hear about this problem of adversarial examples, there's probably a bunch of defenses that will pop up in your head, like, oh, we could do this, and this is definitely going to solve the problem. It turns out that for virtually all of these things people have thought about and have looked into, it's very easy to find something that does help at least a little bit in making models more robust. But we haven't yet found a defense that really truly helps against an attacker that is adaptive, in the sense that if the attacker knows or has some kind of guess on what kind of defense you've actually deployed, then all bets are off again. And so some examples of this are, well, ensembles. You might say, well, we have multiple models that are sort of individually fragile, let's ensemble them and try to get a robust model out of them. But as we've seen before, because these adversarial examples tend to transfer between models, it's usually very easy to find a single perturbation that fools all of the models in your ensemble. So that usually doesn't help that much. There's a bunch of pre-processing that people have looked into, like sort of blurring the image a little bit, or taking multiple crops, or compressing the image with the goal of sort of getting rid of some of these perturbation artifacts. And this actually works fairly well against a specific attack you might try it against. But then again, if you adapt the attack to take into account that some of these pre-processing techniques might be happening, then it's fairly easy to create perturbations that are sort of immune to this as well. There was a nice work by Nicholas Papernot, one of my co-authors, a few years ago, where they tried a concept called distillation, which is sort of to train a model based on the outputs of another model and try to get it to be very, very confident about the points that it actually classifies. And this was actually shown to also not really solve the problem if the attacker was sort of aware this was happening. There's been ideas of generative modeling, so sort of trying to actually model the true distribution that the inputs come from, and just sort of rejecting anything that is seen as adversarial. So there's actually a whole line of work on trying to just detect adversarial examples, not necessarily trying to classify them correctly, but just detect that an image was perturbed and then just reject it. And this has also been shown to be mostly useless when an adversary is adaptive and can sort of make perturbations that are specific to the defense that was deployed. And then finally, one thing I'll actually be talking about today, and that actually seems to be a bit sort of the most promising technique, both from a formal and empirical perspective, is adversarial training. And so we'll talk about this, and we'll see a bit how well it does. You can guess that it might also not work as well as expected. So adversarial training. So what's the idea here is that while we're training our model, so we can feed it an image, it might classify it correctly, we get some loss out of it, and it's basically some kind of positive feedback loop where whenever the model makes good classifications, it's going to reinforce its belief that it's learned the correct representation, and whenever it misclassifies, it will have to sort of tweak its representation somehow. So what we will do during training is that we'll just take the current state of the model, generate a bunch of adversarial examples for the current model being trained, and then just re-inject them into the training set and sort of tell the model, hey, you're making mistakes here, so fix this. And then we just repeat this process. And so you can basically see adversarial training as a specific way of doing data augmentation when you train a model. So throughout training, you perturb inputs and sort of tell the model that, no, it shouldn't be misclassifying this point. And so by doing this iteratively, you'd hope that the model would converge to a state where it has sort of learned a robust representation. And there's a bunch of trade-offs here that have become quite apparent lately with some very nice work on sort of small data sets in this space. And so the first thing you have to decide when you do adversarial training is what kind of attack you'll be using to actually generate these perturbations. And here there's essentially two different directions you could go in. And one that was actually popularized by an early work by Ian Goodfellow was to say, well, let's just compute the model's gradient and take sort of one big step, this sort of single step into the direction of the gradient. And the sort of the idea behind this is to think of the model as being essentially a linear model, in which case just taking a single step in the direction of the gradient is actually just the optimal thing to do. The thing is, the models we train on most data sets today are not linear, and so this is just a sort of gross approximation of what the loss landscape actually looks like. And so if you want a perturbation that's much stronger in the sense that it will really make sure that the model misclassifies with very, very high confidence, then what you do is essentially the analog of, again, of gradient descent is that you take many small steps, many iterative small steps to actually maximize the loss. And of course, the trade-off here is speed, in the sense that if you just do one single step, you're computing the gradient once, you're just doing one perturbation. So this is fairly fast, and on the other hand, sort of the more iterations you do, every time you incur a large cost. And since you're doing this for every image on every training step, it can very, very quickly just become intractable. And so this is where I'm getting at, is that when you use sort of these weak single step attacks during training, you don't really end up with a model that's fully robust, although it does help, and I'll come to that in a second. But the nice thing about this is that it's a fairly scalable process. So you are essentially, in some sense, you're incurring a factor of about 2 compared to regular training, and so. Yeah, you can easily scale this to most tasks people care about today. On the other hand, if you really do, if in every training step you really make sure that you compute sort of the worst case perturbation for the current model, there's a very nice and recent paper by Alexander Madry and his co-authors at MIT that showed that for somewhat smaller data sets like the MNIST digit data set, you can actually make this converge. It's going to take a very large amount of time, but you actually can learn models that seem robust to certain classes of perturbations, even in a white box setting. So even if the adversary has full knowledge of the model and its parameters, it actually won't be able to find perturbations that fool the model in most cases. But so far, we don't really know how to make this scale to sort of larger data sets, like the ImageNet data set that these images of animals actually come from. Okay, so let's look at how this single-step adversarial training, so sort of this crude approximation that scales well, how well this does on a data set like ImageNet. And so this was actually a work from Alexei Kurkin and his co-authors last year, where they trained such a model, and they found that it worked reasonably well. It converged after a little while, and it attained an error rate on sort of clean data, on just non-perturbed data of 22%, which is sort of very close to the state of the art you'd expect if you didn't do adversarial training. And then they found that if they tried to attack their own model with these same sort of weaker attacks, they incurred some error, so they're not quite as good as on clean data, but it's much better than if you hadn't done adversarial training, in which case you'd get maybe like 80 to 100% error on such attacks. The weird thing we noticed, and that was sort of what kickstarted this work, is that if instead of attacking the model in a white box setting, you attack it in a black box setting, so you just don't really look at the model's parameters at all. You just compute on a holdout model and then look at how well the model does, the adversarially trained model. Well, it actually does worse than in the white box setting, which is somewhat confusing in the sense that you're now looking at a weaker attack that uses less information about the model that's being attacked, and it suddenly does better. And so there seems to be something weird going on here, and that's what we investigated. So to understand what's happening here, let's look at how you could actually sort of taking one large step in the direction of the gradient. And one way of doing this, and that's sort of what you'd aim for, is to have a model that is actually robust for every point. That is, every point is actually far from the decision boundary of the model. And so whatever perturbation, small perturbation you add to these points, you won't actually make them flip class. What actually seems to be happening in practice is something that we call gradient masking. So this was a term coined by Nicholas Papernotte in an earlier work, where essentially what seems to be happening is that the model actually still learns a representation that is very fragile, in the sense that all the points lie very close to the decision boundary and can very easily the class can very easily be flipped by a small perturbation. It just turns out that the gradient, so sort of the local information about which direction you're supposed to move in to actually generate a perturbation that's adversarial, is completely off, and just sort of generates perturbations that are absolutely not adversarial. And this is sort of due to the non-linearity of these models. And it's something we can nicely visualize by sort of plotting here what we plot is the loss that the model incurs when starting from a data point. So here at the 0.00, that's our original data point. And then we're going to see what happens when we move in two different directions. And here on the first axis, we're actually moving in the direction of the model's gradient. So this is equivalent of doing a white box attack. And we see that sort of, even if we go relatively far in this direction, so if we perturb the image quite a bit, the loss doesn't really change. It goes up a little bit, but not by much. And so we actually end up with a point that's not adversarial, that's still correctly classified. On the other axis here, we're looking at the gradient of the holdout model. So this is the equivalent of a black box attack. And here we see that expectedly, as we make the perturbation larger, the loss sort of steadily increases. And so at the end, as we've seen, we actually ended up with an adversarial example in a lot of cases. So when you sort of look at this picture from afar, you're sort of wondering, well, why doesn't the gradient just point in this direction where the loss seems to be sort of smoothly increasing. And so actually, if you zoom in to what happens in the very, very close vicinity of the data point, you actually find that weirdly, the model sort of learned a representation that has these kind of wiggly curvatures near the training points that just make sure that if you're looking at information, curvature information in very close neighborhood of the data point, the sort of direction of steepest descent, what the gradient will give you, is actually not at all the same. It really doesn't represent the way the loss evolves overall. And so in a way, instead of learning a model that's actually robust, that sort of actually learned a strong defense, it somehow learned some parameters for which the attack is actually just very weak. And so that's kind of a situation we'd like to avoid. One thing we showed, which is follows pretty obviously from these observations, is that you can actually make these single-step attacks that just take a single gradient step. You can make them quite a bit more efficient if you randomize them. So if you first just take a small random step away from the data point, so you just perturb the image sort of randomly with a very small amount of noise, and then you compute the gradient at this perturbed point, and then just move once again. You take a large step in the direction of the gradient. Suddenly, you again get a much higher error rate, and so it seems that the adversarial training here is really kind of overfit to a very specific type of attack, and isn't really robust as soon as you look at attacks that are a little bit more sophisticated. So in order to come to our contribution here, this ensemble adversarial training, let's just look quickly at what's really going wrong with this sort of single-step adversarial training. And so here what we're doing when training is that we're asking the model to minimize its loss on perturbed points, that it sort of perturbs itself given its own gradient. And there's essentially two ways we can minimize this expression. And one solution would be to have a model that's actually robust, and so that actually incurs a small loss for anything that comes out of this attack. The other solution is actually to just make sure that the attack is very, very bad and just produces points that are not really adversarial in any way. And we call this as a degenerate minimum of this problem, and so we'd like to avoid this happening. And the solution we propose is to actually just make sure that we decouple the attacker and the defender in this scenario. So the problem here is that we're sort of asking the same model to take the role of the defender and the attacker, and so it seems that it just learned to make the attack as weak as possible, so it has to do as little work as possible in the defense side as well. So what we suggest here, which actually ties things nicely with this black box threat model, is to take a model that we're training and not only just train it in isolation, but also just take some other pre-trained models for the same task. And then we're going to generate adversarial examples during training that come from all of these different sources. So we'll still have adversarial examples computed from the model being trained, but we're also going to have adversarial examples that just come from these pre-trained models. And then we're just going to inject all of these back into the training set and train this way. And what we gain from this is that now the model is actually, in every training step, it's asked to classify images for which it has no influence on what kind of perturbations were actually computed. So it's sort of, if it wants to minimize the loss, it actually needs to learn to classify the perturbations that come from these pre-trained models correctly. And so the results are actually very positive. So here we trained two different models, an Inception v3 model and an Inception ResNet model on ImageNet. And so if we look on clean data, and that's the left plot, we see that all the models do reasonably well. So the blue model is the one from the previous work by Alexei, and the red and green one are the ones that we trained. And so in the middle column, when we look at white box attacks, it turns out that Ensemble Adversarial Training with the same model architecture can make things slightly worse. And this makes sense in that we're sort of not really overfitting to this specific attack anymore. So we're actually maybe doing a little bit worse against this specific attack, but this is in a white box setting. If we look at the black box setting on the far right, so the threat model that we really care about, it turns out that we actually learn to do better there, so to really resist perturbations that come from other holdout models that we didn't consider during training at all. And so this was the goal. And so we see that we actually can sort of avoid the issue that arises with standard adversarial training. There's still a gap, obviously, between the error rate on clean data and the perturbed data, and that's I guess something that we'll look into in future work to see if we can actually get this gap to be as small as possible. We also looked at some stronger attacks, and so here, sort of the same as what happened in previous work, we found that with this strategy, we can't actually get a model that is truly robust in a white box setting. So if you know the model parameters and you put in the work to generate perturbations that really maximize the model's loss, you will be able to fool it. So it hasn't learned a representation that is truly robust to all perturbations. But in a black box setting, it does fairly well. And so there was this competition for adversarial examples that completed recently, that is co-located with NIPS this year, and was organized actually by Alexei and Ian Goodfellow. And so Alexei, who organized most of the conference, he actually submitted our Ensemble Adversarially trained model as one of the baselines for the defense category, and where it actually got the highest score in the first development round. After that, we actually released the model, and so it sort of turned into a white box setting, and people started targeting it, and at which case it sort of dropped down the leaderboard a little bit, but still a lot of the teams that submitted to the final round actually made use of this model as usually as part of just a larger ensemble to get some extra diversity. And so to conclude, I'll just mention some open problems still in this space that were uncovered either by our work or by other works in this space. So the sort of main question, I think, is how far we believe we can go with this adversarial training paradigm. So as I alluded to a bit earlier in this talk, there was actually a recent work that showed that you can attain white box robustness to certain classes of perturbations. But there's sort of still two main caveats here. Is that one, this is very expensive, so you're really incurring a cost of maybe like 100x compared to regular training, and this is just on a simple digit data set. We don't really know what to expect when we move to something like ImageNet. The other caveat is that we don't really know what the right metric is to evaluate adversarial examples. So what people have looked at in the past is things like L-infinity metrics, so you're sort of allowing every pixel to just be changed by a small amount, or some L2 distance between adversarial images and the original ones. But then you can consider sort of more elaborate things an adversary could do, like he could take an image and rotate it slightly, or he could change the contrast, the lighting, and things like that. And it seems that if we really want robustness against all of these things, we'd somehow need to enumerate them and enumerate sort of all the valid perturbations an adversary could try out, and that just seems like a hard thing to do. So maybe there's ways in which we could learn what the right metric is, and there's some definitely a big open question there. And this is sort of also tied to the bigger open question, I think, which is whether we can actually say anything formal about these adversarial examples, sort of really get a good understanding of why they exist, which seems somewhat tied to actually understanding how deep learning works, which is still a big open question in this field as well. The other big question is, of course, why these adversarial examples transfer. So why two different architectures that were independently trained tend to learn these sort of same non-robust representations. Okay, so with this, I'll conclude, and I'm happy to respond to some questions. Thank you. Okay, so I'll start with a question by Nicholas, which is, could you please recall the difference between white and black box? Yeah, sure. So in a white box attack, what we consider is, so there's a model that you want to attack, and as an adversary, you actually get access to the model. So you know its architecture, you know its parameters. Basically, you know its training data, you know everything that makes up the model. And so this means that you can very, very easily just solve the optimization problem of finding perturbations that maximize the model's loss and make it misclassify. You can just do this analytically and very efficiently. In a black box setting, you don't get access to the model. In our paper, we sort of consider that let's say you know the model's architecture, because it might have been described in some research paper or something, or you might have a guess of what it might look like, but you don't know the model parameters. And so you can't actually compute any gradients or sort of, yeah, do the optimization problem in a black box setting. And so here, the best strategy that we know of for an adversary is actually to just train their own model that's completely independent from the one they're trying to target, and then just taking perturbations for their own model and sort of hoping that they'll also work for a targeted black box model. And with sort of high probability, this actually turns out to be the case. The question about Salman on whether these concepts are related to neural cryptography. This was a concept of using two neural networks trained adversarially to encrypt data. In a way, yes. So neural cryptography is actually, it's part of a more general framework of that's, for some somewhat unfortunate reason, is also called adversarial training, in part because Ian Goodfellow was actually one of the people who launched both of these ideas. And when you look at other ways in which adversarial training is used, most prominently in generative adversarial networks or in neural cryptography, there the idea is to sort of train two models, one against each other on a specific task. And you can actually do this for adversarial examples as well, in the sense that you could have one model learn to generate adversarial examples and have another model learn to defend against them. And this is actually something we saw in this talk, is that when you do adversarial training the way the original paper sort of mandated, you're sort of conflating both of these models into a single one. So you're asking the same model to play the role of the attacker and the defender, and that can sometimes lead to these sort of degenerate minima that we encountered here. And so it seems that if you actually would split up the models and have one model play the role of the defender and one model play the role of the attacker, you could probably get rid of these problems. It's something that's been proposed to use this sort of dual model adversarial training framework for adversarial examples, but as far as I know, no one has really looked into it yet, whether it actually works and whether you can get the two models to converge. Okay, so a follow-up question by Nicholas asking why the higher error rate that we find in a black box setting rather than a white box setting is strange. So this is usually just from a general security point of view. When you look at the strength of an adversary, usually the more information an adversary has about the system he's targeting, the stronger his attacks you'd expect to be, in the sense that, yeah, if you're targeting, say, if you want to write malware for a particular system and you have zero access to the system, you'd expect to do not as well as if I give you all of the design specification, I let you look at the code and so on. And here, this is true in the case that if you actually get access to the model in a white box setting and use a sort of strong attack where you really take very fine-grained steps to maximize the model's loss, you'll do much better in a white box setting than in a black box setting. However, when you use these sort of weaker attacks, these just single-step attacks that take one big step in the direction of the gradient, here suddenly it seems like the extra information that the model gives you, so the gradient you can compute, is actually misleading you when you do an attack. And so this is kind of what we found surprising here, is that in some sense, as an attacker, you can do better by just ignoring some of the information you might get from the model. The question by Wade about how adversaries fool malware machine learning models. So this is probably referencing some papers I mentioned at the beginning of the talk. So the way a machine learning model will work for malware is not that different from the image case, in the sense that you'll have a bunch of input features. In the case of images, these are individual pixels. In the case of malware, this would be maybe different static features extracted from the code, or some metadata and so on. And an adversary can, under some constraints, sort of tweak these input features as well, and try to find sort of a minimum set of features that he has to tweak in order to get the classifier to suddenly say that a certain piece of malware is actually benign. So the example I gave in the talk was for Android malware classifier, where some of the features that the classifier uses are just specific options that are set in the application's manifest file. And so you'd sort of expect these features to have a relatively low importance, because they probably don't really tell you much about whether an application is malware or not. And yet it turns out that by tweaking just a few of these features, you can actually get a piece of malware to suddenly be recognized as benign, just because the model seems to put too much weight on any individual feature. And so by just tweaking things a little bit left and right, you can get the model to misclassify without actually changing the application behavior. Another question by Nicholas, asking if reinforcement learning or metaprogramming could improve the results. So I'm not I'm not fully familiar with the research in this space, but I know there's been some people that have looked into adversarial examples in the reinforcement learning setting, and it turns out you can actually create adversarial examples there as well. So there was a few nice works that looked at game playing agents for, say, Atari games, and found that there as well, by just tweaking the inputs to the reinforcement learning agent a little bit, so sort of showing it just slightly perturbed video game screens, they could get the agent to perform completely badly, so it would just lose the game as soon as you perturbed the signals it got a little bit. And so there's probably some ideas from reinforcement learning that we can use to increase robustness. But again, if we allow the adversary if we assume the adversary knows that we're doing this and he can sort of adapt his attack accordingly, often that just doesn't seem to be enough. So Salman's asking whether machine learning models that train on encrypted data is a good way to mitigate attacks. So that's an interesting question. So if you assume that you're training on a task for which getting access to training data is actually hard, then it might actually be difficult for an adversary in a black box setting to even train his own model. If training data is sort of easily available, then the fact that you've encrypted your training data, but I have other training data that sort of comes from a similar source, it might not be the same training data, but it might just come from a similar distribution. If I can do that, then encryption probably won't help you much, because I don't really need access to your training data in order to launch a black box attack. If we are in a setting where maybe you have data that's very hard to come by, and I as an attacker don't have access to this data, then things might be a bit more tricky. There's been some work by Nicholas, one of my co-authors, showing that you can actually try to reverse engineer a black box model just by interacting with it. So sort of by sending it inputs and getting back predictions, you can try to locally train a model that's somewhat similar in its input-output behavior. And for this, you don't necessarily need access to training data, or at least not to a lot of it, and you also don't need a lot of interactions with the target model to learn a local representation that's relatively faithful. And then they show that by attacking your local model, you can again sort of transfer these attacks to a target. As far as I know, it hasn't really been demonstrated yet whether these kind of attacks scale to very large data sets and models, but it seems that it might be possible. And yes, I can provide a link to this paper as well. Thank all of you for your attention, and wish you a happy Sunday.